So to help you understand what we are doing here, we are going to take a simple example. This is a E-rod. It's a car that's used for riding on off-road conditions. It's an electric E-rod, E for electric, right? And as part of that whole electric process, one of the key things we have to do is reduce weight. Like the more weight you reduce of the car, the more efficient the car becomes. To help reduce the weight of the car, there are many different parts you can be looking at that can be optimized for weight reduction. One of the key parts that we thought we will show is this knuckle that helps control the steering on the tires right here.
This is the original part, cast steel, which is the weight of it is about 2.5 kilograms. And what we will show in the process is how you can re-engineer and reimagine this part while making sure that it's still manufacturable. So we're going to use different techniques, different technologies, such as additive, to lightweight this and to make it even stronger. So here you can see the result of the process. The redesigned part looks very organic, and it's lighter, and which is most interesting, it is better performing, it is stronger, it has higher durability.
So the first step we will do is actually do a 3D scan of the part. So as we get the part, we'll kind of get a complete scan of what that part is like, how it's shaped, what are the holes in it, how does it look, right? What are the features of that part? Once we have got the 3D scan, we actually bring it inside our design tools. So that's our first step. Second step, then we will bring it into our design tool and run through the entire process to see how that part can be optimized. So think of it as AI-driven technology, where we will give it certain conditional parameters that this part needs to have this many holes, it needs to have this much curvature, it needs to have this much structural strength, and based on those parameters, the system will return back an optimized design for us. So within a few minutes, it will run through all the different permutations and combinations of that whole design. Now to make this part, what do we need to do? Right, this is where we will then look at the manufacturability of that part. You just don't make one part at a time, because this is going to be additively made, this is 3D printed. We may make 5 of these at the same time, right? So really optimize the whole manufacturing process. So we'll kind of look at all the support structures that will be needed to make that part and actually go through that whole manufacturing process, right? So all of that is done inside one integrated software digital environment, right? Where you're doing the scanning, you're doing the designing, you're doing the topology optimization, you're doing the simulation. This is where you do the complete process planning to kind of see how that part itself will be made, and what are the different items you will need, what are the resources you're going to need to make that part. So once you've done the planning, we have the closed loop technology and the closed loop manufacturing process available, so that you can see how the part was actually made on your production shop floor, and bring that information back to your planning process. So you really have that closed loop.
Even the data, because constantly there are adjustments even on the shop floor that are happening, that data can also go upstream, so to say, so that even the designers or the programmers have access to that latest data, so that you always work with the latest manufacturing package, which is critical, because in 2 weeks, in 2 years, you can do the similar part. So having access to the data that was used to actually machine the part is critical.
So what we're doing here is subtractive machining of our part. So now you'll see here we have 4 parts on a build tray. Laid out how we have it, 4 parts with all the features facing to the outside. We're able to machine all of our critical features in one setup. So from the build tray, we now put it into the machine, and we can access all of our key features. Now you'll see we also have extra features added on here. You'll see this is our part here, but in the center we have this trumpet looking shape. We actually designed this and made this for a few reasons, right? This is going to support our part while we machine. It's going to keep our part stable, so there's going to be less chatter, less deflection, less vibrations, right, when we machine it. And at the end of it, we're actually able to cut it off. So As we watch this machine move, you'll see this is a exact replication of the machine on the floor. So this is what we call a digital twin. Now, this digital twin is actually being driven from the machine code-based simulation. Right here is the actual G code driving the simulation on the right-hand side. So one more thing that you're able to do is you're able to drive this machine using external G code. So even if you have legacy code, you can drive this digital twin using your legacy code.
Once we are done trying to figure out how we're going to make that part, we actually bring it to a digital simulation of the physical machine itself. Over here, we'll actually take that part and we'll figure out every detail of how that part is going to be machined in a virtual world, in a digital world. In the digital virtual world, it's a zero cost environment, right? We can break the part, we can break the machine, we can break the tools. It doesn't cost us. We can check everything out before we actually take it to the physical machine. So this is actually is a digital machine also, by the way. It's not a real machine, but it's a 100% replica of what a physical machine would be like. And you can hear the sounds as well. In fact, even everything on this machine has been replicated in how it would be in real, with a real controller. And what you're seeing now is that part being machined, and you can go through the whole process of making that part, and ensuring that all of it will go through properly. And now we're looking at the CNC, the controller. All of this is one integrated environment, ensures that there are no issues, there are no data losses, there are no problems that could happen in the transitions. It's all one integrated, seamlessly integrated environment, ensures 100% throughput and highest possible qualities.